assignment 2, I'm going to be explaining 4 of the problems. So let's just dive into problem 1. Essentially, we're given this data set where basically this data set, it has like handwritten digits that ranges from 0 to 2. And we're trying to get a model to decipher or distinguish between the digits. So first and foremost, we're going to be running a PCA on this data, and then we're going to project it in 2 and 3D dimensional space, and we're going to show you what the figures look like. So we went ahead and import the respective packages because that's what we're going to be using throughout the code. So in like NumPy, we're just using for like matrix. Pandas, we use it like for like loading and handling like data sets as data frames, which you'll see later when we're using stuff to read like CSV files. So the problem did specify using matplotlib plot. So right here, we had to import this library, which is right here. And essentially from sklearn, we kind of use it just to standardize some data. We wanted the mean to be 0 and the variance to be 1. And then for this guy here, I imported because I wanted to compute some eigenvalues and eigenvectors. Yep. And then for this last one, I actually used it to graph it for the 3D space, which you'll see later soon. So this part right here, I'm just like loading a data set. So essentially this reads an SV file that contains like those pixel values of the handwritten like digits like from 0, 1, and 2. Yeah, so then now the DF, which stands for like the data frame, actually holds like the features and the labels. And speaking of features and labels, so this is what I define for labels, and this is what I define for features. Now, just for clarity's sake, labels is like the last column of the data set I found out, and then it contains like the labels for the digits 0 and 1, and so we're going to be using them as 0, 1, and 2 to classify those labels. And then for features, that one just simply represents the pixel data for each sample. Again, I mentioned that we standardized the mean and standard deviation. So I set the mean to 0 while the standard deviation just to be 1. Great. And then next we actually calculate the covariance. Now, the reason why we had to calculate the covariance is because it helps us describe like how each feature varies with every other feature. So it's like important to identify like the direction of the maximum variance. And just to let you know, like the maximum variance means like principal components. So that's why we had to calculate covariance matrix. And then again, we had to use the calculate the eigenvalues, eigenvectors, and we use the eigen method, and we extracted from the covariance matrix that we just defined here. So then, actually, next we had to so before we even use those eigenvalues and vectors, I kind of want to just talk about like why are we doing this step. So the eigenvectors actually represents the principal direction, which is the axis of the data. But then the eigenvalues, they show how much like the variance is along each axis. So after getting those like eigenvalues and eigenvectors, we sorted them in descending order. And that's because like the first few represents like the most important variance direction of the data. So after selecting like the top eigenvectors, which this is what these are. This is just for the 2D and the 3D. So after selecting like the top eigenvectors, we then project it into our data. So here, this big chunk of code represents us plotting the 2D PCA, and then this chunk of code here represents plotting the 3D PCA. So just to kind of go in here, this is us actively plotting. We're grabbing into data, making this part into a data frame, storing it in here, saying this is our labels. And we're making it a type int. We're gonna set the color 0. Class is gonna be represented as blue. Class is gonna represent as green. The 2 class is gonna represent as purple. And then this is us, like for each digit. Go ahead and plot it in its respective colors. And this is just creating the plot. Same thing happens to 3D, and then we're just going to show it. And so I'm going to show you what it looks like. So essentially, this is the 2D space PCA, and this is the first axis 1 and axis 2. So here, this blue dots represent the digit 0, green dots here represents digit 1, and then the purple dots here represents digit 2. So you can see for the most part they're kind of pretty much clustered in its own respective space. Now, could it be better? Yes, it could be better, but essentially what this represents is that the first 2 principal components actually captures like the direction of the maximum variance. So yeah, you see some overlaps. It just means that if there are some overlaps, that not all the variance is captured by just 2D space. So if we take a look at it in 3D space, this part represents the PCA axis 1, PCA axis 2, and then PCA axis 3. And so here, there is a little bit of better separation you actually would see. But for the most part, it kind of pretty much looks the same, to be honest, as 2D PCA plot. So that just shows that the more principal components you have, the better it distinguishes, so the model distinguishes between the digits. So you see it's a little bit less overlapping between this part and this part, which is pretty good. So that's pretty much, this is my interpretation of it. So overall, we just know that PCA helps reduce the data dimension, but it also retains the most important variance, which is why we use like the 2 components. So 2D, PCA actually helps us plot some level of class separation. We do see some overlap, which is slightly disappointing, but as we increase the dimensionality to 3, we see a little less overlap. So just as a reminder, like PCA is like an unsupervised, so it focuses on variance and not necessarily on like the separation between the digit class. So that's pretty much about problem 1. If we go on to problem 2, it asks us we're going to look at the same data set, and for how many eigenvectors are needed to capture the 99% total variance of the data. So we're going to investigate that, and then we're going to plot the average reconstruction error for each of the digit class. So a little briefly, this is what we're going to be looking at later. So going over the code real quick, still using the same data set. We're importing some of these libraries, pretty much similar to problem 1. And I just imported them separately in its respective code blocks, just because if, for instance, like something is wrong here, I rather just run this code if I want to produce the output of this code specifically, which is why I imported the packages. Technically, if I already used the packages in problem 1, I don't have to reproduce it here, but just to make sure that problem 2 code runs smoothly, I just input it here. So kind of same tune where we're loading the data set and we're extracting the labels and features. We're also standardizing the mean to be 0 and the standard deviation to be 1. We calculate the covariance matrix and calculated the eigenvalues and eigenvectors. We sorted them. Now this is where we start differentiating from problem 1. So for this part, we calculate the cumulative variance, and we find like the first index that hits the 99% variance, we retrieve it and we store it as the 99 variance, the variance underscore 99. And then essentially, I kind of just grab like arbitrary numbers that ranges from like 1 to all the way to the variance 99. I found out actually early on that the variance underscore 99 was 170, which is why I placed it last. I printed it earlier. I just removed it because I just want to have it together with the graph. So here I printed to capture 99 variance. We needed this many eigenvectors. So it was actually calculated much earlier, like around here. I just printed this and I found it to be 177, which is why I went ahead and created like a range from 110, 50, 100 to 150, and then 177. So that's the PCA components values. Now we're just going to go ahead and straight jump into this part, which is defining a function to compute like the reconstruction errors. Now, reconstruction errors, the aim of this is to project data like on the top of the number of components. So when we reconstruct the data from the data set, we aim to like reduce the version. So when we calculate the reconstruction error, we use the mean squared differences between the original and reconstruction data. And then in the end, we ended up kind of just storing it in the average reconstruction error for each digit class. So this is pretty much what we did here. We did like a for loop. We grabbed the top eigenvectors, we constructed the data, and we calculated using the mean. We grouped them and return it. So all in all, really, this computer reconstruction error is aiming to return the reconstruction errors. And we do that effectively here by calling that method and storing into reconstruction errors. And then I just printed it and then I plotted. The X part represents the principal component while the Y represents the average reconstruction error. And this is our little handy dandy legend. And like I mentioned, in order to capture 99% of variance, we need 170 eigenvectors. And so the green represents digit 1, blue represents digit 0, and then purple represents digit 2. Now, I want to point out, yes, as we increase the principal components, you'll notice that the average reconstruction error decreases. And so essentially, by decreasing it, we approach the average reconstruction error to 0, and we find that 99% of the variance is captured at around 170. And so that's great. But what else can we pull from this data? Well, notice that digit 1 already starts off at an extremely low average reconstruction error in comparison to like digit 2. Okay, so let's break that down. Why? Well, digit 1 probably is easier to assess and analyze and to classify than digit 2. And that's because the complexity of the stroke 1 versus 2, it's much easier to assess and identify with digit 1 than digit 2, because digit 2 has more of a complex structure than digit 1. And then you notice like digit 0, it's like in between. It's in between in terms of average reconstruction error between digit 1 and digit 2. Yeah. So overall, we just noticed that the more principal components we have, aka more eigenvectors we have, the more accurate the reconstruction is, aka low reconstruction error. So that's pretty much for problem 3. Problem 2. Now we're going to just jump straight into problem 3. So what it asks of us to do is essentially take the same data set that we've been working with from problem 1 and problem 2. Then we're going to run LDA in 2D space. But then we're going to compare it to PCA in 2D space. And then after that, we're having two graphs here. Then we're going to be answering, will LDA allow us to project the data in three-dimensional space. And then we'll just explain. So same tune, we're importing some packages that we've used before, loading the data, and then we're grabbing it and assigning it to features and labels, standardizing it. Now this part is a little bit different. We have to split the data from 80% training and 20% testing. And we use this method here called train underscore test underscore split. And then we have a function here. And this function just aims to calculate the scattered matrices of LDA. Now, LDA, if I haven't mentioned already, remember that just stands for like linear discriminant analysis. So essentially, when we compute the scatter matrices, it just helps us to calculate between the class scatter and within the class scatter. So you'll see in this in this function, we have something called like SW and SB. So SW stands for within class scatter, and that just deals with measuring how much samples is in each class that varies around their class mean. But if we look at SB, what that does is first of all, it stands for between class scatter, and it measures how far apart the class means are relative to like the overall mean. So basically, both matrices are kind of important when it comes to finding the LDA direction, and that it helps, separate the class. So you'll find that, well, I'll save that point for later. Anywho, so this function here, oh, and if I haven't made it apparent already, that's what this returns. The compute scatter matrices, that just returns the SW and SB. So LDA method is basically a method that performs the LDA projection matrix from training data. And then we're going to apply it not only from the training data, but we're going to also apply it for the training set. So yeah, so when and we're going to use it, we're using it right here. We're using this method. We're passing in train X, train Y, and the number of components. And then we're going to call on it. So then method graph PCA, and then okay, well, I just wanted to double check, but basically this here we're just calling a method just to help graph the PCA, and this is us actively plotting LDA. I just wanted to put PCA in a function, and then and I just wanted to separate it and then call it here. I thought it was cleaner, and then I could have done the same for LDA, but it's pretty much the same thing. And I had to put it into a function and then call it. But anywho, I did, and then we plot it. So here's a side-by-side comparison of LDA and PCA. So you'll notice off the bat is that, first of all, we've seen this graph before. This is from problem 1, and you can see that, there are some bit of clusters between like its digit classes. But if you compare it to this one, it doesn't look as clustered together as LDA. And that's because LDA is really good for separating digits or separating like features in its classes. So essentially, when performing LDA, using the scatter matrices, we find like the axes are best for separating digits in class. But PCA, it's not that good at separating digits from classes, but rather it finds like the axis of a maximum variance, and it doesn't really take into consideration of its classes. So you can just see that like both LDA and PCA projection, when you compare it, that clearly LDA has a better separation between the digits classes, and we can see how well the classes are actually separated. And that's because, right, LDA uses supervising learning, which takes in the labels when going through testing. But PCA doesn't really focus on class separation, but rather focuses on the variance, and that's because PCA looks into unsupervised learning. Great. So our next question is right here. Will LDA allow us to project the data in three-dimensional space? Short answer, no. Long answer, well, no, because LDA helps project data using a specific formula like the C minus 1. So the number of classes that we have here actually is just three, digits 0, 1, and 2. Oh, by the way, if I haven't mentioned, the X stands for test, and then the circle stands for training. And you can see that the X is on top of the purple, and in that case, it just shows that that for each class is actually really well aligned, and it's actually indicating that the model was pretty much successful when distinguishing between the classes. So just wanted to point that out. Sorry about that. Um, but going back to this one, so yeah, LDA follows a simple pattern. Take the number of classes minus 1. In this case, we have 3 classes, digits 0, 1, and 2. And so 3 minus 1 is 2. So the most that LDA can project is in 2D space. Great. So for the last problem. Now, the last problem, just we are given 3 different architectures, network architectures of that. And then we're going to set the activation function into the bottle layer as linear. And then other hidden layers will be as tan. And then we're going to separate our data from 80% training, 20% test. And then we're going to pass through the training and the test data through each of the encoder. And then afterwards, we're going to be using the the 5 nearest neighbors, essentially, the K and N, just to determine the accuracy for each of the network. And then we're going to just go ahead and report back to you of what we ended up finding through the means and the standard deviation. So what does that entail? Well, the code is actually not that long, and this is basically the output of it. For each of the network, we're reporting back the mean standard deviation, and there's 3 of them. So let's just dive into the code and how did we do it. So again, we imported some packages that's already been mentioned. We're gonna just jump straight into a class called AE, but which just stands for auto encoder. Now, we have to create a neural network structure for an auto encoder. And so what that means is that it has an encoder and a decoder. So first of all, what the heck is an encoder? Well, an encoder reduces like the data dimensions, but the decoder reconstructs the input from the encoded data. So here, the encoded data layers here, sorry. Here's where we actually store the encoded layers. And so to do that, we just basically loop through the layers and then apply like the tan activation for all the hidden layers and linear activation for all the bottom neck layers. So then here, right here, is the decoder layer, and for that part, we just build a decoder that pretty much mirrors the encoder structure. And then finally, we grab the self dot losses and we store that the loss of epoch and we store it into this. So we're still in that class, and in that class we have forward and fit. Well, first of all, forward is basically a function that just helps to pass the data through the network. So that includes passing it through the encoding and decoding. But the fit, if I move this guy over here, the fit function, the aim of that is just to train the model, really. I mean, basically it handles training model in terms of it goes over the parameters that we want to entail, like mini batches, the mean squared error, and we're also going to be using an optimizer, which you soon later will find out. It's called Atom. So basically, we load the data into batches, and then for each epoch, we actually perform like a forward pass and then compute the reconstruction loss. And then you would think we're done, but we're actually not. Right here is where we perform the back propagates loss, and then from that we actually update the weights. So, and this part is basically we did a class. We went over the code in class, and this is pretty much how we did it. We just printed a bunch of like the epochs and its loss, and so I just did that over here as well. So now time to get into the actual code that I wrote. So here we're just loading the data using the same data set that we used prior, extracting its features and labels, and then I do want to mention that we did normalize the pixels to 255. And then just like the instructions mentioned that we had to separate the data set from 80% trained to 20% test. Okay. Basically here, we did have to convert the data into PyTorch sensors, and the reason why we did that is because later you'll find that we need NumPy arrays to be translated into PyTorch sensors just for training and evaluation purposes, really. And then here is when I established the architectures that was given to us, and there's 3 of them. You can notice as each of the layer here, like it just gets more complicated. We have more layers to go through, and that's 3 of the networks there. And so also I do want to mention that the shorter the layers are, the smaller network. So essentially AE3 is the largest or the deepest network, I should say. Then after that, we established some training parameters. This part I took it from, again, like from the class code. We have these set of training parameters that I used. So I set the epoch to 200, batching size to be 64, and the learning rate to be 0.001. We're storing all the results into an object here. Okay, so this big for loop, which stops around here, the aim of this truly is to train it and evaluate at each autoencoder. So the aim of it is just to loop through each architecture. We're training it and then evaluating the performance of each autoencoder. And here, where do I want I want to point out right here. So this part right here, this is just initializing and training the model. And then the problem mentioned bottleneck. So for this part, we essentially we are extracting the encoded representation basically of the bottleneck layers for both of the 2 sets, the testing and training. Then we're storing it into here, translating them in a NumPy array, and we're training and storing them into train and test and embeddings. And so one thing I wanted to mention is like just embedding is just a compressed version of the test samples. And then here we are actually computing the K and N. So K and N, the problem established that there's going to be, we wanted to find the 5 nearest neighbors, and we want to run this around 10 times. So essentially we're running a 5 nearest neighbors classifier, and then we're running the bottleneck features 10 times. And then we're storing all that into a list called the KN underscore accuracies. And then essentially this part here, all we're just doing is just printing out basically the mean accuracy and the standard deviation for each of the architecture. And then to do that, we had to convert into a data frame and then print it. And then when I ran it, essentially this is the scores that I got. So you'll notice that the shallow networks had a higher mean accuracy than the deepest network. And the aim, basically, reason why is because the more layers you add, the more complex um, it adds more complexity and it actually confuses the model. And so, because what comes with deeper layers? Well, deeper layer networks just have more parameters, and that just makes it really difficult to train the model. And of course, it reduces the stability of it. So essentially, having deeper network doesn't make it better. It introduces more layers and more parameters, and making it more challenging for us to train the model. But I do want to mention that the standard deviation for all three of them is 0, which basically indicates how consistent our results are across all the runs. So overall, the shallowest layer has the highest mean accuracy of 83%, and but the deepest layer, or the deepest network layer, has about 73%. So definitely the lowest mean accuracy. So yeah, so overall for this problem 4, we basically built 3 autoencoders with using 3 different architectures that has 3 different depths, and then we basically trained them to reconstruct the data set, and then um, we compress them from the bottleneck layer, which is the encoder, and then we use the K and N, just to point out and just classify the digits based on their compressed embeddings. And then overall, we just compare the accuracy between the 3 layers, and we find that the AE one is the has the highest mean accuracy, and therefore it is easier for the model to be trained with using a simple network. Thank you.